Welcome to Lecture 13, The Electrical Heart of Matter. This is the first lecture in Module 3, Plug in, Turn on. And as the title implies, this is all about electricity, or actually electromagnetism. It would be hard to overstate the role that electricity and electromagnetism play in today's technological society. Electrical energy is certainly the most convenient form of energy we have. It's easy to generate, it's very easy to transmit, it's easy to convert into a lot of different forms. It's one of our most widely used important forms of energy. Electric motors power everything from my watch to subway trains to dentist's drills to washing machines. Electricity is everywhere. If I were to ask you, have you used any electrical device today? Your answer is certainly yes. I have a number of electrical devices arrayed here in front of me. Here's my computer. Here's a printer. We'll talk more about how that printer works later. Here's a fan. In a few lectures, we're going to run that fan with electricity made from sunlight. Here's a shaker of salt. What's that doing here? Well, that's also got to do with electricity. Electricity is everywhere. Here's my little clicker I've been using to advance my slides. That is also an electrical device. In fact, it's got in it a laser, which I can point and which is electrical. More on lasers in a subsequent lecture. It's impossible to get through a day in today's technological society without using electromagnetic devices. You yourself are actually electrical. The beating of your heart, the transmission of electrochemical signals down your nerve impulses are electrical, natural electrical systems that make your body work. Physicians use electricity and also magnetism to probe your body, to get signals from your body, to find out what's going on inside your body, and even to heal broken bones. Turns out electrical fields, which I'll describe in a moment, can be used to enhance the healing of broken bones. And even within you, the individual atoms that make you up are held together electrically. Electrical forces join those atoms together to make molecules. Those molecules get complicated like DNA. Even the replication of DNA is essentially an electrical process. What I'm emphasizing in this first lecture, the electrical heart of matter, is the role electricity particularly plays in holding matter together, in formulating the structure of matter, in making matter what it is. I'll talk a little bit at the end about some electrical technologies that use some of these most basic ideas, but I want to emphasize primarily the essence of electricity and how it is that electricity is at the basis of the world we live in. Electricity is really a fundamental property of matter. People say, what's electricity? And the sort of elementary school answer, electricity is a flow of electrons. Well, that's a definition of electric current, and I'll get to that in the next lecture. But electricity is a really fundamental property of matter, and specifically that property is called electric charge. Matter, most matter, is in fact electrically charged. If you start asking me what is electric charge, I'm going to have a little trouble telling you. If you start asking me what's mass, you sort of think you know what mass is. It's kind of a measure of how heavy something is. Well, not quite, because that heaviness manifests itself only with gravity present, and there might be places where there is no gravity present, or places where it seems like there's no gravity present, as we know from the previous lecture, and yet mass still manifests itself as an inertia, a response to forces. It's harder to accelerate a more massive object. I can't give you a real good definition of what mass is, but I can tell you how mass behaves. And both you as a non-physicist and I as a physicist probably have a pretty good gut feel for what mass is. But ultimately that gut feel is based on our interactions with massive objects. And if you ask me what electric charge is, I have to say ultimately it's like mass. I don't know exactly what it is. It's a fundamental property of nature, and I understand it from having worked with it and understanding the rules it seems to obey. There's a big difference between electric charge and mass, and the big difference is there are two kinds of charge. And we happen to call them positive and negative, and that is a nice way to handle things because algebraically it works out nicely with the positive and negative signs. But I don't want you thinking there's something missing about negative charge that's somehow deficient. Positive charge and negative charge are two opposites of the same coin, the yin and the yang, if you were. They're not absence and presence of something. It was Ben Franklin who gave them the names positive and negative, and he made a mistake that every introductory physics and electrical engineering student has probably rued since that day. He called the charge that happens to exist on the electron negative. And the reason that was not such a good idea is because it turns out in the materials we use to carry electric current, namely metals, it's electrons that are moving and carrying the current. And so every time you think about an electron flowing this way, you've got to think about current going that way. It would have been much easier if Franklin had named the electric charge on the electron to be positive, but he didn't. And that's the way it is. I'm going to pretend this tennis ball is a proton and this little green ball is an electron. Proton and electron are very different in some ways. A proton has about 2,000 times as much mass as the electron. It's a rather different kind of particle. An electron is a truly fundamental particle. And there's a teaching company course on particle physics, and you can learn a lot more about that there, whereas a proton is a composite particle made up of 3 quarks, each of which has some electric charge. But the proton ends up having an electric charge of exactly one, what's called elementary charge, one positive elementary charge, and the electron, despite it being a totally different kind of particle, has exactly -1 elementary charge. The charge on the proton and electron are equal and has been verified experimentally to a remarkable precision. And if there was even the slightest imbalance, you would be highly electrically charged, and your hair would be standing on end, and sparks would be flying off you all the time. It's remarkable that these two very different particles have essentially exactly the same charge. And we understand something about how charges behave. Opposite charges attract each other with a force that, like the force of gravity, but it isn't the force of gravity, depends on how far apart they are. Double the distance between them and the force drops to a force as strong as it is. Like the force of gravity that depends on the product of the two masses involved, the force of electrical attraction depends on the product of the two charges involved. And furthermore, the electric force, because charge comes in two kinds, can be either attractive, when the two charges are opposite, or repulsive. So two protons repel each other. If I try to push them together, it's hard to do. This, by the way, is the reason we don't have nuclear fusion as an energy source. The basic problem there, it's very hard to get two nuclei very, very close together and get them to fuse because they're electrically charged with the same charge, namely positive. And there's a law called Coulomb's law that actually describes, in the same way Newton's law of universal gravitation describes gravity, Coulomb's law describes this electrical force, and all first-year physics students learn about that. But I want to move very quickly to a slightly more sophisticated description of how electric charge behaves. And I want to begin by giving you a gravitational example. I introduced gravity by saying the Earth pulls on objects, and that's the attractive force of gravity, and down they go, changing their motion according to Newton's laws and so on. But I'd like to sort of think about that in a little more abstract way. I'd like to say that somehow, right here in space, at this point where I'm putting my finger, there's a special property. And the property is that if I put a mass there, this tennis ball, for example, that mass will experience a force, and it will be a downward force. And how big that force will be will depend on the mass. If I put a bigger mass there, such as this bowling ball, at that same place, it too will experience a downward force. And that downward force will depend on its mass. It will be bigger the more massive it is. And I could describe this point in space by saying there is a force of, in fact, near the surface of Earth, about 9.8 newtons of force for every kilogram I put there. So there's something special about this point in space. Now, it's not so special because this point has the same property, this point has the same property, this point has the same property. If I go very far away, that strength, that force for every kilogram I put there gets weaker. And and if I go to a different part of the world, that force is pointing in a different direction because it's always pointing toward the center of the Earth. What I'm describing for you there is what we call the gravitational field. Instead of talking about the Earth reaching out across empty space and pulling on things, it's more convenient, more philosophically appropriate, and in the context of Einstein's relativity, simply more correct, to talk about the Earth's gravity being a field of influence around the Earth. And I have a picture here that illustrates how we might try to think about that. So here's the field idea. So the old view was that the Earth kind of reaches out across empty space and pulls on an object, say the moon. So there's the old picture. The newer, more abstract field concept says this. It says the Earth creates a gravitational field, this influence, this tendency for objects to experience a force. And the moon then responds not to the distant Earth, 250,000 miles away or whatever, but to the gravitational field that the Earth has created in the vicinity of the moon. So the picture for that would look something like this. Here are the Earth and the moon, and the Earth has created around it this kind of field, and I've illustrated it here by this kind of green glow, although it's not anything you can physically see. And the moon doesn't know anything about whether the Earth is there or not. All it knows is in its vicinity there's a gravitational field, and it's pointing in the direction in this picture to the left, that is toward the center of the Earth, and it results in a force that the moon experiences in that direction. And this sounds like a vague abstraction, but it's going to become really important to talk about fields, particularly in the context of electricity and magnetism. We're going to talk about electric fields, we're going to talk about magnetic fields. And in the very last lecture of this sequence, of this module, we will be talking about electromagnetic fields and how they combine to make waves, including light. So there's the field concept. And the electric field is the same thing. A proton, we consider, creates an electric field. So there's a proton with its positive charge. Now, in the old way, we said, oh, proton reaches out across empty space somehow and pulls on an electron. Now, we're going to say something different. We're going to say the proton creates in its vicinity an electric field, which I've illustrated here by this pinkish-purplish glow. And if an electron happens to find itself in that field, then the electron responds to the field at its location, and that field says, I'm pointing to the left, and I have so many newtons of force, again, the same force unit, newtons, for every unit of charge, because it's charge that responds to electric field, and so the electron responds and experiences a force in that direction. Now, this sounds very abstract at this point, but I'm going to continue to use this electric field concept throughout this module, and by the end, I hope you'll become quite familiar with it. Students in introductory physics start out hearing about this. They think this is very abstract. And suddenly they learn that these fields store energy, and they do experiments with the energy stored in fields, and they see sparks fly when that energy is released, and they come to understand that these fields are very, very real. They have a reality. They're part of the stuff of which the universe is made. In fact, the fields are, in a sense, a manifestation of energy, another form of energy. In fact, you can store energy in fields, and that's a form, if you will, of potential energy. By the way, it's this mutual repulsion of charges, or to put it in the field concept, a positive charge creating a field which exerts a force away on another positive charge, that is why you're protected from lightning by a car's metal body. Often people say, well, you're safe in a lightning storm if you're in a car because you've got those rubber tires insulating you from the ground. That's nonsense. By the time those tires are wet from rain, they're not very good insulators. The issue is the car, at least most cars, increasingly they have fiberglass in their bodies, but cars with metal bodies, with a metal frame around you, the lightning may deliver an enormous chunk of charge to the car if it strikes the car, but because all those charges have the same sign, they rush apart, they get as far apart as possible, and they stay on the outer skin of that metal, and you're completely protected. Here's an example of that kind of thing happening. This is a picture taken at the Boston Museum of Science. The Boston Museum of Science has what was, in the middle 20th century, one of the larger particle accelerators for studying the properties of the atom and so on, the interior of the atom. And the early particle accelerator simply generated an enormous electrical voltage, more about exactly what that means in the next lecture, and particles were accelerated through that very large electrical voltage difference to very high speeds, crashed into atoms or whatever, and we could see the results and explore the interior of atoms. Well, when this particular machine, it's a Van de Graaff accelerator, was retired, the Boston Museum of Science acquired it. It's in their Hall of Science. And here we see an operator standing in a cage, and the cage looks something like a bird cage, and it's pretty much open, but it has a wire mesh cage to it. And the operator, putting up his hand, is actually drawing a giant lightning strike from one of those balls. It's an artificial lightning strike toward his hand. But the lightning strikes the cage, the charge is deposited all around the outside of the cage, and the operator is completely, perfectly safe. There's a whopping, big, horrible lightning noise going on with this. It sounds very scary, but the operator is perfectly safe. And you, in your car, in a thunderstorm, are safe for the same reason. So that's electric charge. Electric charges produce these electric fields, and these electric fields then exert influences on other electric charges. I sort of skipped a point earlier when I said, well, this electric field is measured in the force per unit of charge, just like the gravitational field is measured in the force per unit of mass, force per kilogram. But I haven't told you yet what the unit of charge is. The unit of charge is named after the French physicist Charles Augustin de Coulomb, for whom Coulomb's law is actually named, although several others were involved in the discovery of that law that involves the forces between electrical charges. And 1 Coulomb is about 6 million trillion. That's about 10 to the 18th, 6 times 10 to the 18th, if you want, 6 million trillion electron charges. So the unit we use for electric charge, the Coulomb, that's just an artificial human invention, the Coulomb, happens to correspond to about 6 trillion million electron charges. As a physicist, I would prefer to work in units of this fundamental charge. Nature gives us the charge on the electron, but we talk in practical terms of the Coulomb. And I'll talk about the Coulomb again in the next lecture when I introduce the idea of electric current. But just to give you an example, if you have a 100-watt light bulb, which has a current of roughly an ampere flowing through it under normal conditions, and an ampere is a coulomb per second, then there's about 6 million trillion electrons going by a given point in the wire or through the filament of that light bulb every second. So that's how we measure charge. Now, this lecture is called The Electrical Heart of Matter, and the reason it's called that is because matter, as we know it, owes its structure almost entirely to electrical forces. As I stand before you like this, gravity is pulling on me. It's pulling on my arms. Why don't my arms fall off? Well, they don't fall off because there are electrical forces that are acting to counter gravity. In our everyday world, almost every force that we deal with is in fact, other than gravity, is in fact a manifestation of the electric force. Almost, but not quite. Occasionally we have magnetism. Occasionally nuclear forces are involved directly in our everyday lives, although of course they're involved in the structure of matter at the most fundamental level. But most of the forces we deal with are electrical. Friction, that's an electrical force. The force I get when I stretch a spring, that's an electrical force. The force that's holding me together, that's an electrical force. The forces involved in the replication of DNA or the burning of gasoline, those are ultimately electrical forces. So electrical forces play an enormous role. And what happens is, to build up the structure of matter, protons join together with neutrons to make atomic nuclei. Now, protons are positively charged. They repel each other. Neutrons are neutral. They don't repel or attract. So how do you build a ball of stuff that is either positive or neutral? Why don't the protons go flying apart? And the answer is there must be some other force, and that force is the nuclear force. And we'll get to that in lecture 34 when we talk about nuclear things. But so that's outside the realm of this particular module, but somehow with this nuclear force, protons and neutrons bind together to make an atomic nucleus. Those nuclei attract electrons, and one gets orbiting, if you will, around the nucleus as many electrons as there are protons in the nucleus. And I really shouldn't describe it as orbiting, but it's convenient to think of that as sort of a first approximation. Really, we're dealing here with quantum physics, and the electrons are kind of in a statistical swarming cloud around the nucleus. But the point is, the number of electrons must equal the number of protons. And it's the electrons that determine the chemistry of a particular atom, a particular substance. And so the number of protons in the nucleus ultimately determines what kind of thing one is. Are you hydrogen? Are you oxygen? Are you carbon? Are you uranium? That's determined by the number of protons in your nucleus, and that's called the atomic number. And a very simple model of the atom might look something like this. Here I have a proton at the center, and I have a couple of orbits, and there are electrons going around, and this might be a very crude model for, well, it's got 2 electrons, so it'd be helium, but it's a very, very crude model for helium. There's a lot wrong with it. But this was one of the first serious models of what an atom must look like. So that's an individual atom. Now, atoms tend to be electrically neutral because the positively charged protons attract to them negative electrons in equal numbers. So why do we go anywhere from there? Well, even though the electrons make the atoms neutral, the electrons can still be shared among several nuclei, or in some cases an electron can be transferred from one nucleus to another, making each of them positively charged. For example, I have here some salt. Okay, a little salt shaker, I shake it out, there's some little salt grains. If you looked at them very closely, you would see that they were little cubes. How does that work? Well, in the case of salt, salt is a so-called ionic crystal. In salt, here's the salt crystals. Now you can see them. If we looked inside one of those salt crystals, we would see negative chlorine atoms which have given up electrons to sodium and made the sodium more positive. And the structure of salt then consists of these individual so-called ions, atoms that have lost or gained an electron, bound together nicely now because they're charged by those electrical forces. So there's an example of how the structure of matter, and in this case the nice cubical structure of the salt crystals, is ultimately linked to the way those atoms bind together. Another example, slightly more complicated chemically, is the structure of oxygen. An oxygen molecule consists of two oxygen nuclei and most of the innermost electrons around each nucleus. But the outer electrons are in kind of a quantum mechanical swarm again, but if you thought of them as little moving particles, they're swarming in and out among those nuclei, and they tend to concentrate more in the center, which is why I've made this picture darker in the center, and consequently that tends to bind those two nuclei together. That's called a covalent bond, and that's what holds oxygen together, and many other simple substances, nitrogen, carbon dioxide, so on. Now I want to mention something else about the electrical force. The electrical force is extremely strong. It's about 10 to the 40, or a 1 with 40 zeros, stronger than the gravitational force. What I mean by that is the following. If I take two protons, and I calculate the repulsive force between them at some distance, and I calculate the gravitational attraction, which they have after all because they both have mass, the electrical repulsion is about 10 to the 40, a 1 with 40 zeros after it, times stronger. Electricity is a colossally strong force. Gravity is colossally weak, and yet in our everyday lives we don't tend to notice electricity very much, and we sure notice gravity. We worry all the time about falling. We rarely worry about some strange electrical thing happening to us. Why is that? Well, the reason is the very strength of electricity is part of the reason why we don't notice it. The very strength of it, plus the fact that there are two kinds of electrical charge. Because what that means is large agglomerations of matter tend to be uncharged. If they were charged, they would quickly attract the other charge and become electrically neutral. So everything from atoms, molecules, on up to something like the Earth tend to be very close to electrically neutral. They would have enormous electrical effects if they weren't. So in this picture I show at the left, the round circle is a sort of symbolic picture of the Earth in each case. There are two kinds of charge, and on the Earth they are essentially there in equal numbers at all places. Not quite, by the way. The Earth actually has a very slight negative charge, but it's very small. The imbalance between the number of electrons and protons is almost insignificant. Plays a slight role in the atmosphere and in thunderstorms and so on, but otherwise insignificant. There are two kinds of charge. We have a neutral planet. On the other hand, gravity, a very weak force, 1 with 40 zeros after it times weaker, nevertheless has only one kind of, quote, gravitational charge, only one kind of mass, and the only force is attractive. And so all the masses that make up the Earth are attracted together, making this great big round sphere, and the gravitational effects of the Earth are very significant. So we tend to not notice electricity just because it's so strong, it tends to form neutral structures. Now, you might say, well, if all these structures are neutral, how does anything interesting happen? Well, they may be neutral, but nevertheless, they may have slight imbalances in where the charge, the electrical charge in a structure, is distributed. And that effect becomes very important in forming molecules from atoms and more complicated structures from molecules. And I want to give you just one example, and it's really quite an important one. It's the water molecule, H2O. The water molecule looks symbolically something like this. There's the big negative oxygen, there's the two small positively charged hydrogens, and although the hydrogens aren't fully one electron's worth of charge, or one proton's worth of charge, the sharing, the covalent bonding that I described before for oxygen, occurs here with water, and it occurs in such a way that the electrons spend most of their time near the oxygen, so there's essentially a negative end of the water molecule. It's where where the oxygen is, and there's a positive end. That's where the hydrogens are. So even though the water molecule is electrically neutral, if it finds itself in the vicinity of another charge, say a positive charge down here, there's going to be a repulsion between the hydrogens and that positive charge, and an attraction between the oxygen and that charge, and the hydrogen is going to flip like that. And then it's going to feel an attractive force. And that's kind of a residual attractive electrical force that exists not because the hydrogen molecule is charged, but because it has an imbalance in the way the charge is distributed. It's not distributed symmetrically. And by the way, for water, that imbalance is very large compared with most other common substances. And that's the reason that water is a very good solvent. You put things in water and they tend to dissolve. The reason is that electrical effect, the big electrical effect of the water molecule, it's called its electric dipole moment if you want the technical term, that effect is very large in water, and it can rip apart the molecules of other substances, and that's how things dissolve in water. Another important example here is the microwave oven. An electric field that is rapidly changing direction. In a microwave oven, that's happening about 2.45 billion times every second. can grab those water molecules because they respond to electric fields because they've got this imbalanced charge. Here you see it responding to the electric field of that positive charge. And they can flip the water molecules back and forth. And that flipping motion, as all the water molecules jostle against each other, ultimately results in the energy from the microwaves being transferred to heating. Much more of this in Lecture 28, which will be Physics in the Kitchen, a good part of which I'll spend on microwaving. But let me just point out, I have a microwave oven over here. Put the water, and notice the water's in a paper cup. No problem, because the paper cup's molecules are not particularly structured like this. They don't have a particular imbalance in the way the electric charge is distributed, so they don't respond to the microwaves. So in the oven it goes, press the button, and the microwaves are jostling the water molecules back and forth in there. So a microwave oven works because of this unusual property of the water molecule, that its electric charge is not distributed at all symmetrically about it. And I want to end here with just a couple of other examples of technologies that make use of this simple fact of electric charge. If you've got an inkjet printer, which is the most common kind of home printer certainly, it works by electrically charging little tiny drops of ink, applying particular electric fields by means of electrical voltages applied to little tiny electrodes, accelerating them and steering them so they hit just the right spot on the paper. So the electrically charged drops are accelerated by electric fields, and that's basically how an inkjet printer works. Your printers at your office, however, may be laser printers, and they work by a slightly different mechanism, but also involving electric charge. And I'm going to take a minute and show you how that works. By the way, also Xerox machines, the whole process of xerography is a process, dry copying is a process that intrinsically involves electric charge. And here's how it works. Here's a sort of symbolic picture of the essence of xerography or laser printing. What we have at the left is a light-sensitive drum or roller. It's light-sensitive in the sense that when light lands on it, it becomes electrically charged at that point. And when light doesn't land on it, it doesn't. And somewhere there's a lens, and then there is in this case of a Xerox machine, there is something we're going to image, in this case the letter T. If this were a laser printer, by the way, the lens, or not so much the lens, but the T would be replaced by a laser that was playing across the drum in a particular pattern to make the image that was going to be printed by this printer. So what happens to make the printer work? Well, the printer is is electrically charged. We shine light through where the T is. The light-sensitive drum then loses its charge everywhere except where the T is, and we drop on these so-called toner particles. That's that black dusty stuff that you have to put in your printer every so often. And because the charge remained on that light-sensitive drum only where the image was supposed to be, the only place those toner particles stick is there in that T pattern. And now we have some heated rollers. We heat the roller up and we run a piece of paper under it. I'm not going to show all those processes. And these toner particles, which are little bits of plastic, which again stick. They're not themselves initially electrically charged, but because they have charge imbalance, they stick to the charged parts on that drum, and then they are melted into the paper. If you've ever had a laser printer or Xerox machine go wrong on you and you had to take the paper out, you might have picked up a piece of paper that looked like it had a perfect image on it, and you wipe your hand across it and it's totally smeared because they haven't been melted into the paper at that point. But the essential process in laser printing or xerography, Xerox copying, is to cause a pattern in charge on this light-sensitive drum to correspond to the image you want to make. Then you deposit these toner particles on there. They stick by this simple electrical attraction, and then you roll it onto your paper and melt it into the paper by means of heat. I want to mention one other last example of technology involving simple electric charge, and that's in cleaning our air. In the United States alone, 30,000 people are estimated to die each year, or at least die prematurely, from the effects of particulate air pollution, most of it from coal-burning power plants. It would be a lot worse, however, if most of those power plants weren't equipped with pollution control devices called electrostatic precipitators. And in an electrostatic precipitator, two metal plates, or sometimes a thin metal wire near a metal plate, is given a very high voltage charge. And if you put a very high voltage on a piece of metal, a lot of electric charge accumulates there. And the electric fields get very, very large, and those electric fields get large enough to ionize, that is, to remove electrons from molecules in the air. Those molecules attach to particulate matter in the exhaust smoke from the power plant, and then they become attracted to these electrical plates. And in the electric precipitators in big power plants, the plates very quickly accumulate huge layers of this dust, this particulate matter that otherwise would have gone into the air. These giant mechanical clappers come along and clap them, and all that stuff falls down into a hopper where it's carted away by trucks and used for things like road surfacing and so on. A remarkable, simple way of removing otherwise harmful material from the air. You may have a small version of an electrostatic precipitator as an air purifier at home. Now, those are all examples that use electricity basically in the simple form of charged matter. And we talk about simply moving this charged matter around. That's not most of the electricity we use, however. Most of the electricity involves organized flows of electric charge through conducting wires, and that will be the subject of the next lecture.